So I titled my talk, "A LiDAR in Every Garage," and I hesitated at putting a question mark at the end of that because it's still a technology in development. So people think of this in the context of self-driving cars, but there's actually a whole series of innovations that are being developed under the name of ADAS, or Advanced Driver Assistance Systems. And there's a level structure that was developed by the Society of Automotive Engineers. And level 1 and level 2 are actually quite common. An example of level 2 would be the automatic parallel parking function that some cars have. Level 4 and 5 are more the self-driving car. That's a vision that I think is still quite a ways out. But level 3 is coming very quickly. And those are vehicles that can drive themselves, but the software really isn't able to handle all circumstances. So the driver's still in the loop. But one thing that's important about level 3 is that you need the entire sensor suite for autonomous driving at that point. And so that is not very far away. To get an idea of how this business is developing, there's a prediction that the market for automotive, or LiDARs in general, will be about $6 billion by 2024. And 70% of that would be the automotive market. Another interesting number is right now, in the last year, this year, the estimated market for LiDAR is about $300 million. And I would guess most of those are still going into automotive applications. None of those are going into cars that are on the market that you or I would purchase. They're all going into software development platforms, which gives you an idea of how big a challenge the software development is. So the consensus is that you need a sensor fusion approach with multiple sensors that complement each other, as well as providing some redundancy. And the big three for the exterior of the vehicle at longer ranges are radar, cameras, which are basically CMOS imaging technology, and LiDAR. The radar has the advantages of being a longer range sensor, immune to weather phenomena, which is very important, but inherently a lower resolution technology because of the longer wavelengths involved. Cameras are very high resolution in terms of spatial resolution, but they're inherently a 2D technology. And for these kind of navigation applications, requires a lot of signal processing after the sensor. LiDAR is actively illuminated, can operate day or night, has relatively high resolution and long range, and is a very low latency technology. And the depth information is available very quickly. But there's a big cost difference. The radars have come down to sort of this $50 range in high volume. Cameras are quite a bit less, and the LiDARs are still rather expensive. So I want to give a quick introduction to the history of automotive LiDAR. LiDAR goes all the way back to the invention of the laser almost. But in the automotive context, it's actually a fairly recent history, and it started with the DARPA Grand Challenges. And the first one was in 2004. It was near Barstow, California, out in the Mojave Desert, a closed course. There were no finishers of all the teams that were entered. They did it again in 2005. People had done a lot of improvements on their sensors and software, and there was one winner of the 2005 Grand Challenge, which was an autonomous vehicle called Stanley, developed at Stanford University. And it actually had 5 industrial sort of line scan LiDARs on its roof, as you can see. But another entry that was in that competition that didn't finish was from Velodyne Acoustics. And David Hall at Velodyne Acoustics had built this rotating LiDAR system that you can see on the roof of the vehicle. Again, they didn't finish, but people were so impressed with the sensor, he was asked to commercialize it and make it available to other teams. The next and the last DARPA Grand Challenge was in 2007. It was an urban environment, much more complex, and there were 6 finishers, 5 of whom had the Velodyne LiDAR as their primary sensor system. And this became more well known to the public around 2011 when the Google cars started showing up with that Velodyne LiDAR on the roof, the LiDAR costing quite a bit more than the car. And again, these are software development platforms. So let's take a closer look at that LiDAR system. It's an ingenious design. It actually spins 360 degrees, and there's an optical module that's the transmit assembly, and there's part of it that's the receiver assembly, and there are 64 hand-aligned individual lasers in the transmit assembly, and again, 64 hand-aligned photodiodes in the receiver assembly. And its real claim to fame in terms of its utility is that horizontal resolution number of less than a tenth of a degree. And as you see on the right of the screen, that's what's called a point cloud. That's a visual representation of the data that's collected by the LiDAR. And that high level of resolution is why it's been sort of the gold standard for more than 12 years. Now, to be fair to Velodyne, their later offerings are much more compact. That system at the bottom of the slide is about 75 millimeters tall. So there are critics who wonder whether you really need LiDAR. And only a couple of weeks ago, Elon Musk said at an investor conference that LiDAR is a fool's errand. Anyone relying on LiDAR is doomed, doomed. And then he went on to say some more things that basically are making the real issue, which is the LiDAR was too expensive for an early adopter like Tesla, so they went on ahead without it. So just to give you an idea of the difference here, I want to show a short video clip. This is 77 gigahertz radar data. It's courtesy of a company called Autonomous Stuff, who not only engineer these software development vehicles, but they develop software, and this is a visualization software that's really a guide to the engineers as to what the sensor is doing. And so these are the radar returns. Now, the size of the balls are not the real indication of the spatial resolution. That's more like the spacing. And they're color-coded to show Doppler information. And that sign went over, you saw a flash of different colors. So let's compare that with a current state-of-the-art LiDAR. This is a Ouster system. This is a similar system to a Velodyne, and it's a spinning, mechanically scanned LiDAR. And you see the very high spatial information and how that would correlate very well with video data. And the upper frames are the raw data feeds, the lowest of the gray frames being the actual spatial or depth information. So our company actually does not build LiDARs. We're lower in the food chain. We supply illumination systems to various types of LiDAR manufacturers. But we get to talk to a lot of people. And one thing we noticed a couple of years ago, there was a remarkable consensus around the requirements. Assuming you're not going to have a LiDAR on the roof of your car that's spinning 360 degrees, you're going to have a long-range forward-looking LiDAR system, and then ones around the side and back of the vehicle that are much shorter range. So that's that two different resolution requirements. And the more challenging one, of course, is the long-range one. 200 meters is kind of the canonical number, but we have seen some requests for even longer range out to 300 meters. The automotive environment is very severe, and one of the most difficult things is the temperature range of -40 to 125 C. But the thing that surprised us was the cost expectations. For that longer range LiDAR, less than $200 per unit. And that was the high end. Some people were saying it had to be lower than that for it to actually get widely deployed. So that brings up the question, will there be a LiDAR in every garage? It won't be from a lack of trying. There are estimated to be about 90 startups right now developing LiDAR technology of different kinds. On top of that, all the OEMs, the actual car manufacturers, have their own R&D programs, and most of what are called the Tier 1 suppliers, who do most of the real technology development for automobiles, are developing their own LiDAR systems. So almost all the industry thinks that it's necessary for autonomous driving. And fortunately, there's many ways to build a LiDAR. And the race here is not really for a better LiDAR. They're already pretty close. These rotating systems do pretty good, but for a good enough, cheap LiDAR. So we can classify LiDARs into two basic types, flash or scanning. And a flash system is basically a camera. No moving parts. You have a 2D detector array that defines the field of view of the system and the spatial resolution. And then you need the illumination from the laser system. But it's not necessarily a high brightness laser, but it does need to be very high peak power because you're illuminating the entire field of view of the scene at relatively long ranges. The other types of systems, including these rotating ones, are scanning systems. And there the spatial resolution is defined by the divergence of the laser beam in the far field. And the field of view is defined by the scan angle of the system. It does require a higher brightness laser system. And they come in either one-axis or two-axis versions. And the one-axis version is really a line scan, so you need a linear detector array as well. So scanning has a lot of issues. Mechanical scanning, of course, there's weight, reliability. If you compare the different mechanical options, the rotating systems actually look pretty good. That's a very robust system that will probably be around for a while to come. But almost everybody agrees that ultimately it's not going to work for wide employment. There are systems based on MEMS scanning mirrors. MEMS imposes some pretty severe optical constraints. If you want to be vibration resistant, you have to have a very small aperture and have limited scan angles. Any of the folded path architectures with more than one scanning mirror, you've got a very difficult manufacturing challenge. So there's a lot of work going into solid-state scanning approaches using various types of electro-optical, even acousto-optical and other phenomena. All of those have their limitations, usually having to do with the usable aperture or particularly low scan angles, sometimes high loss, and almost across the board challenges with managing extreme temperature ranges. And then you can classify LiDARs by the type of detection. And almost everything out there right now is a direct detection system using a photodiode or an APD biased in the linear gain range. These are pulse systems. It's a direct time of flight measurement. You need a very fast rise time pulse, and you're electronically measuring the time of return from the objects. And your noise limits are the background light and the amplifier noise of the system. And all the current scanning and flash systems based on direct detection are eye safety limited in the near infrared range. That pushes a lot of the competing designs to look at longer wavelengths. And of course, if you go past 1.4 microns, the fluid in your eye is absorbing the light and the tolerance goes up quite a bit. So you can be eye safe at long range, however, you still use a lot of optical power. And at those wavelengths, that pushes a lot of the designs towards diode pump solid state lasers or, fiber lasers or fiber amplifiers. And there are flash systems. That's what's shown on the right of the screen. That was published recently by Voxtel. These are very nice high-performance systems, but it's a very expensive technology, DPSS illumination laser and an InGaAs-based array. So the big innovation that I think is going to make a difference here is the rapid development of silicon-based APD arrays, sometimes called Sputter Arrays, operating in Geiger mode for photon counting. This has been progressing very rapidly. They're developing high-resolution arrays. An example is in the lower section of this slide. That false color image is a 300,000 pixel spat array, and it's operating at 940 nanometers, which is a pretty expanded red response for this kind of technology. And they're getting, with flash illumination, out to past 250 meters. Now, they are very background sensitive, so that image was actually taken at night. The other frame on here is from that same Ouster scanning LiDAR that I showed the footage earlier, and it has a spat array. So it's also that technology is also being used for scanning systems. Now, 940 is especially interesting for silicon compatible illumination systems because there's a water absorption dip in the solar spectrum at 940. But it requires that you have a relatively narrow bandpass filter, and you have a laser that can stay within that bandpass over these temperature ranges. The other system that is being developed by many companies are coherent detection systems. And this is my simplified depiction of a coherent LiDAR. People are building demo versions of these using telecom components at 1.55. You have all the parts you need, and then you put a 2D scanning system in front, and you have a very high performance LiDAR. With coherent detection, you can reject background light very efficiently. You have your noise limit is basically the shot noise of the local oscillator, which is part of your primary beam that gets split off and mixed on the photodetector. And something I haven't talked about, you're immune to crosstalk from other LiDARs. So there is concern about if everybody's driving around with a LiDAR and you're going to be pinging each other. So for direct detection schemes, there's an assumption there probably has to be some additional coding in the LiDAR system. However, the coherent detection also requires a very high performance tunable laser diode that can do a linear chirp and has coherence links sufficient to handle the automotive ranges. So how do you make this kind of system inexpensive? Well, there's a major advance going on in the area of silicon photonics over the last few years. And for coherent systems, this is especially attractive because now you've got a monolithic guided wave structure that eliminates a lot of the possible issues with acoustic and thermal phase noise in the system. And some of these processes are CMOS compatible. They're built in 8 or 12-inch silicon processing lines, so you have economy of scale. There's still a lot of problems to solve. You need still this high-performance laser. Currently, the demonstrations, that's an off-chip laser. There's a lot of work from the communications world on heterogeneous integration, putting those lasers on silicon. But if you do an optical phased array, which is very practical now for this very high coherent source, you end up with actually a relatively large chip with 3-5 parts grafted onto it. So it's still an expensive proposition, and it's going to be a while. We have to see how quickly this matures. Now, there's another category that's usually not thought of in this context, and that's the time-of-flight cameras. These are based on fairly conventional CMOS imaging sensor technology. The original players in this are companies like PMD and Soft Kinetic, which got bought by Sony, Panasonic, people that make digital imaging sensors. And what you do is you have an integrating sensor now, so you're not looking at the return pulse rise time. You're integrating light with different time delays between the integration windows, and from there you can do a ratio and reconstruct in a depth map of the image information. So originally these designs were multiple pixel designs, like shown up here in the corner. So obviously you take a hit in resolution because you've got subpixels that take up more area than single pixels. But with the advent of global shutter cameras, which are popular for consumer use, with fast global shutter technology, you can do this in a frame-by-frame fashion and have slightly different timing delays as you have a pulse laser illumination. And then of course the other thing is they've migrated these to having longer infrared response, so they're usable outdoors at 940 nanometers instead of the original 850 nanometer type application. So they're very inexpensive, and another big selling point, these are multi-mode sensors. They can do visible monochrome or RGB, as well as IR illuminated monochrome and the time of flight sensing. The disadvantage is they're inherently a short distance sensor due to limitations on the integration times. So this is probably the solution to that short range LiDAR of 10, 20, 30 meters out. So I want to say a little bit about what we do and where we fit in the food chain. So we are a fabless semiconductor laser company specializing in vertical cavity source emitting lasers. We have a unique proprietary flip chip bonded architecture where we can make both the anode cathode contacts on the same side of the die, so we're back emitting. The back of the die is electrically completely inactive, so we actually fabricate, in some cases, micro optics, sort of single micro lens per laser, and that allows us to do beam shaping, divergence control, and also we can do addressable arrays with multiple zones. Here's an example. This is actually now an obsolete part for us. This is a 300 watt peak power. We now have a 600 watt peak power with the same footprint device. It's for low duty cycle, running 10 nanosecond pulses, specifically for flash LiDAR applications at 940 nanometers. And it's really two devices on the same substrate. These are 2 by 2 millimeter die in this device. Each one has 150 lasers on it, and they're connected in a row in series, as depicted down here. And that's for high slope efficiency for this very low duty cycle operation. And in many ways, this is can be thought of as a long range LED with narrow line width and narrow divergence. And the reason for that is there's 1,500 multi-mode VCSELs, all mutually incoherent. And so you get a far field like this. It's very low speckle, very smooth illumination like you would get from an LED system. And another aspect of this approach is we can engineer in eye safety because it's an extended source. And using the IEC standards, as you get closer to this device, these sources no longer are contributing to an exposure in the same area of the retina, and they become effectively independent sources. So you divide the problem by 10 as you get in closer. And this looks like the same part, but it's a completely different animal based on the same technology. So this is a device optimized for those time of flight cameras that I talked about. And it's a parallel series architecture, still 10 die, but they're connected electrically different through the submount and optimized to give 100 watt output, but much longer duty cycles in the 1 to 5% range. So in conclusion, I think it's highly likely that automotive LiDARs will come down in cost enough to be in every vehicle. And it's really improvements in silicon detection and integration that will be the key. It's also likely that there's not just one winner because of the nature of the automotive business wanting independent supply chains. There's a lot of historic relations from OEMs to tier 1, so there'll be competing technologies for quite some time. And of course, at these price points, these sensors would be applied to many other applications. So I've shared a number of opinions that are my own. I would recommend you don't take these as investment advice because that would be a fool's errand. And I'd like to thank my colleagues at TriLumina and also Autonomous Stuff and Ouster for sharing that data.